Welcome to this lecture. In the last lecture, what we covered was the spherically symmetric evaporation model, right? And before that, we did that what led to the d square law, and we developed some of the relationships that when the spherically symmetric model is useful and things like that. But as we know that when if you look at the screen, that in most of the cases the droplets are injected in a very high speed kind of a gas flow field, right. So, this is gas flow field and this is the droplet. So, if you look at a zoomed in view of the droplet, that means we are isolating the droplet, right. What kind of a flow you would expect? There will be some flow going around it like this, right. It will be almost like flow over a spherical object, like what you have done in your fluid mechanics. So, because of this flow field that is created, okay, it is apparent that there will be some motion that will be created inside the droplet, some kind of a motion will be created, right, some motion, some internal motion has to be created, because this is not a solid sphere anymore, right. So, it is a droplet. So, there has to be some motion, and that motion happens because there is a relative velocity between the gas and the liquid, right. The droplet's own velocity and the velocity of the gas flow field around it is different. So, as a result there is shear that is created along the surface, right. As a result of that, there will be a flow that will be generated inside, right. The magnitude of the flow will be low, but as we will find out in due course, the liquid phase Reynolds number is not small. Okay. So, we will see to that what that exactly means. So, in most of these applications, therefore, the droplet therefore is moving with some relative velocity. So, if we define something like a Reynolds number, okay, for the gas phase with respect to the gas phase, we will call it Re, but here I am writing it as Reg just for the sake of clarity. It has to be a function of the relative velocity, right. It has to be a function of the droplet diameter, right, okay, and it has to be a function of the gas properties. Gas properties means density, viscosity, etc., right. Okay. In most of the cases you will find that this Reynolds number is of the order of 100, okay, 100. So, it is laminar still, okay, but it is not 1, okay, or below. So, whenever you have a Reynolds number in that particular region, what do you expect to see? If this is the droplet, what do you expect to see when you actually have a Reynolds number like that? You will have some kind of a boundary layer that will develop around the droplet, right, that is gas phase boundary layer, is not that so? The gas phase boundary layer will develop, right. So, one will be the momentum boundary layer, one will be the thermal boundary layer, depending on what is the gas phase Prandtl number is, right. Now, most likely if, for example, if the gas is air, the gas phase Prandtl number will be of the order of 1, right. So, therefore, these two boundary layers will perhaps coincide with each other, right. So, you can have a gas phase boundary layer thermal or momentum or viscous, right. Okay. So, this Reynolds number value therefore creates that kind of a boundary layer effect, right. So, beyond that it is all potential, right. That is what normally we are accustomed to seeing, right, that it is potential flow outside, only in the boundary layer you have all these effects, right. If you recall your fluid dynamics course, there you already have done, say for example, if there is a flat plate boundary layer, right, what happens? This is how the boundary layer evolves, right. So, here it is potential, right, okay, and here all the effects are confined to this particular region, right. So, here you have the velocity varying like this and things like that, correct, if you recall your fluid dynamics course, right. So, here also something very similar thing actually happens. So, the boundary layer, there is a gas phase boundary layer that exists, okay, and it is quite natural also to see two other things. One is the liquid vaporization rate, right, the vaporization rate rate increases with RE. Okay. Now, if you have a clear idea why this happens, let us try to step back and explain that why should the vaporization rate increase with Reynolds number, right, with Reynolds number going up. If you take a cup of tea, how do you actually cool it? Okay. Sometimes we blow air, right, we try to blow air over the surface of the tea, right, to cool it. Okay. That is big, but if you keep a cup of tea open to this ambient, it will cool down, right, it cool down after some time, but in order to cool it faster, what do? We blow air, right, and what does that actually do? It basically blows away the accumulated vapor that is around the droplet surface, and that is how it actually promotes. So, it is basically a convection effect, it is not a diffusion effect, because if you recall earlier what we did was that how does the diffusive transfer happens, this vapors get from the droplet surface and they form a layer, right, of high concentration vapor around the droplet, but and after that there is a diffusion gradient which takes away this vapor, okay, slowly with the that is the diffusion flux to the far field, right, and that is how it relieves the vapor concentration here, so that more liquid can escape, right. Now, if you have a convective flow that is happening, it will blow away this vapor, okay, much more conveniently, right. As a result of that, your vaporization rate should actually increase. So, that is one of the key important points. So, it increases. The other thing is that the shear force, this we already mentioned, shear force induces liquid phase internal recirculation. Got it? Okay. So, these are the two prime things, and there exists a gas phase boundary layer. Does there exist a liquid phase boundary layer also? You bet, there also exists a boundary layer in the liquid phase, right. The structure of that boundary layer, these are very hard things to compute, but we will see what we can do about that, right. Okay. So, these are the two important things that we have mentioned over here. And then let us look at the next one, that so there have been many people who have given that in a steady state or in a diffusive environment there is a certain evaporation rate, right. Now, can we actually prescribe some evaporation rate for this convective environment, right. So, Rans-Marshall, and you may have heard the name, is called Rans-Marshall correlation. Okay. So, Rans-Marshall gave a correlation in which m dot is given by m dot SS. SS is basically nothing but the steady state, so 1 plus 0.3 Prandtl number to the power of 1/3 to Reynolds number to the power of half. This is for, this corresponds to a spherically symmetric droplet, right. So, you know the spherically symmetric droplet, you know what the analysis is. If you know what is the Reynolds number value and what is the Prandtl number, right, these are all gas phase, remember, we can actually predict what will be the mass flux, the revised mass flux. Okay. So, as a rule of thumb, can you see certain interesting features coming out of this particular correlation? The first interesting feature is that we already prescribed through the d squared law and things like that and related things, okay, that m dot SS was already kind of a function of d square, right. Okay. It was a function of d square, right. Now, Reynolds number to the power of half, if we write it, that is a function of what? That is d to the power of half, right, scales. So, your m dot basically scales as d to the power of 3/2, right, because it is a multiplicand of this with that, is not that so, right. So, if you multiply the two, so this will be a d to the power of 3/2 for large RE. However, if the Reynolds number value is very small, right, this term becomes negligible. Okay. Say if Reynolds number is of the order 1, okay, and Prandtl number is already of the order 1, then what will this term be? This will be of the order of 0.3, correct. Okay. So, if the Reynolds number is very less than 1, that means less than 1 means we are slowly going to the pure diffusion case, right, that if the Reynolds number value is say 0.1, right. So, this factor now will become 0.03, right. So, it is only 3% compared to this, right. So, there is only a 3% increment. Similarly, if the Reynolds number decreases faster, this m dot actually approaches m dot ss, right. So, in other words, if we plot the evaporation flux, okay, it goes from d to the power of 3 by 2 to something like d to the power of 2. Right. Okay. This happens if your RE becomes very small. Got the idea? Got the clear cut idea of what this could be, right? Huh? So, this is for large Reynolds number, it is d to the power of 3 by 2, large, that means Reynolds number of the order of 100, because when it is of the order of 100, this is 10, so 0.3 into 1.4 I think, right, into 10. So, it will be something like 3 into 1.4, right, 3 into 1.4, around 5, scales around 5, right. So, it is, so this is 1, this is 5, okay. So, we do get a lot of increase, right, in the m dot. So, m dot increases by almost 5 times compared to the steady state situation, right, when Reynolds number is of the order of 100. Got it? Okay, clear on this part. So, now that we have made this clear, okay, in many practical situations the Reynolds number remains high for most of the droplet lifetime. Can you guess why? There is another trick to the whole thing, okay, right. So, Reynolds number, as we know, is a function of the droplet diameter raised to the power of half, right. So, if the droplet mass reduces by 8 times, say for example, okay, 8 times the droplet mass reduces, right. So, the actual diameter reduces by only 2 times approximately, right. So, the Reynolds number change that you are going to have is going to be minuscule, even if your droplet shrinks a lot, right, because one is volume, okay, the other one is basically your Reynolds number is basically square root of this. So, it does not change by much. So, the Reynolds number, if it is of the order of 100, it remains around that order throughout the droplet lifetime, okay, for almost part of the droplet lifetime. Got it? Okay. Now, there are several other things to this whole tale. Okay. The Reynolds, so the droplet can also, when the droplet is injected into a flow field like this, right. So, the droplet can actually rotate, it is free to rotate, right, it is free to roll, right, okay, and this is rotation about that axis, is free to roll, okay, and it is free to spin, okay, whatever you can call it, okay. All these things the droplet are perfectly capable of actually doing, right. But most of the analysis is you will find that people assume that there is an axisymmetric flow, right. How feasible is that? We will look at it, okay, in a little bit, that whether it is feasible or not. And another leap of imagination that people normally take is that the droplets are spherical. Now, this is true in some cases, not always, right, because droplet deformation and atomization can happen, right, and it is a very strong function of the flow field as well, right. So, it is not like that the droplets will always remain spherical, but that is the rule of the assumption. Now, based on this, let us look at the PPT of the flow field that we are going to see in the droplet. Okay. So, based on those assumptions, that what we said, axisymmetric flow field, then the droplet actually does not retain its spherical shape, okay, and the droplets do not really turn in the flow, no rotation as such of droplets, okay, got it. So, based on these assumptions we can see some of the interesting regions that what we believe is going to happen in the flow field. So, this is the outer flow field, this is the free stream that you can see. Okay. So, this is basically the gas liquid interface. This is what is happening in the interior of the droplet, the liquid streamline. This is basically the gas phase boundary layer that we talked about, right. Okay. And this is the liquid boundary layer, this is on the other side. This also we said, right, there exists, right. Okay. Now, based on if this is what the situation looks like, let us see what are the regions in this particular flow field, right. So, there is of course an inviscid free stream region which is marked as 1, right. This is inviscid free stream, right. So, there is no effect of any viscous thing. This is pretty much what happens if you analyze any flow over an obstacle, right. Far field is always like a free stream. Then there is the gas phase boundary layer, this is marked as region 2, okay, and the near wake region. Okay. So, you can see that this is the gas phase boundary layer is marked as 2 over here. Then there is the liquid viscous layer and the liquid internal wake. So, this is the internal wake in the liquid and this is the corresponding viscous layer. So, this is termed as 3. Got it? Okay. So, the liquid boundary layer and the liquid internal wake, and then there is the what we call the toroidal core. Okay, the toroidal core, okay. Now, in this toroidal core it is rotational, the flow is rotating, but it is virtually shear free. Got it? Okay. So, that is called, represented by something called a Hill's spherical vortex, right. So, that is basically your region 4. Got it? Let us recap, okay, that the free stream region is denoted as 1, right, no viscous effect. The gas phase boundary layer is denoted as 2. Let us, where is the eraser? It may not be visible. So, this is 2, got it. Okay. So, this is the gas phase boundary layer, the liquid boundary layer and the internal wake region there, right, this whole region that you see, this is basically called region 3, okay. And the rotating toroidal core that you see, what is denoted as spherical vortex, right, it is rotational, but it is virtually shear free, right, and it is represented by the well known Hill spherical vortex solution. So, that is the 4 regions, okay, that you can mark when the droplet is actually showing all this kind of motion, when it is injected in a gas phase flow field. Got it? Okay. So, in order to solve this particular problem, you need to kind of take into account all these parameters, right. You need to solve the gas phase boundary layer, you need to solve the liquid flow field and the liquid boundary layer, you also need to know what is happening elsewhere, right, in the far stream. Of course, the actual task is a little bit more difficult, okay, and it is not very easy to do, okay, but we will see what happens. Okay. So, this actually, let us end the show here. So, I think you got the idea that what this thing exactly means, right. Let us close this, let us go back to our journal entry. So, now coming back, so let us now try to investigate a few of these estimates, right. Like for example, we said that there is no rotation of the droplet and there is axisymmetry of the flow field. So, therefore, we have stated basically 2 postulates, right, that this can happen if the flow is axisymmetric and the droplet does not show any rotation, okay, then there can be two corollaries essentially. It can be based, it can only happen if this is true. The characteristic time for rotation in flow, right, is long, and I highlight the word long, compared to the transit time of a gas parcel, right, parcel around the droplet. You got it? So, what does this essentially means? That if you see that the droplet is rotating, right, so it takes a certain amount of time for the droplet to rotate itself, right. During that time, if a pocket of gas actually passes over, right, that liquid sphere, and if that time scale is very short compared to the rotational time scale, okay, then we can say that the effect of rotation is negligible, okay, so to say. Okay. So, that is why I said the characteristic time for rotation in flows is long compared to the transit time of a gas parcel, right. And the second corollary is that the fractional change in friction force, and why this is important? Change in friction force is negligible, and it should be of the order of 1 over the Reynolds number, right. Order means that it is of the similar order. When we say order, we do not mean the exact number, we mean the scale essentially. So, where does the friction comes into the picture? Okay. See, a droplet can only rotate if there is a torque, right. If there is an axisymmetric flow field over the droplet, then there cannot be any torque as such that can be produced, correct. So, there has to be a net moment due to some variation of the flow, some asymmetry, some pulsation, something, right. There needs to be something of that sort. Okay. So, there is a need to have velocity gradients there is a need to have velocity gradients, okay, to have asymmetry in the flow. Okay. So, that asymmetry leads to torque, got it, okay. And this torque is further dependent on the friction forces, and friction forces we know that depends on the velocity gradient, right, from the normal viscous shear. Okay. So, friction force, so velocity gradients leads to asymmetry, leads to torque, which is due to the origin of this friction forces over here, right. So, we have to show that these two things are correct, but before we show that, let us look at the drag that is developed on the droplet, because we have talked about friction. Let us do the drag on the droplet. Okay. Now, the drag on the droplet is simply can be written as, writing it fast, where UR is basically the relative velocity, this is basically the absolute velocity, CD is equal to 12 by RE, where RE is based on radius rather than diameter, okay. And R is basically the droplet radius. It is a very simple equation, right. This is how you would write if you inject not just a fluid blob, but something like that, like a solid particle in a flow field, right. This is how you would write that rate of change in velocity of the main fluid blob is dependent on the drag force, where the drag force is not dependent on the actual absolute velocity, it depends on the relative velocity. As you can see, as the liquid velocity increases, right, slowly this relative velocity will become negligible, right. That is what happens, that is how a droplet is actually entrained into the flow field. Okay. So, if you do the okay. As I said earlier that this particular form is more or less valid because the Reynolds number do not really change significantly even if there is a large reduction in the mass. Okay. It reduces by less than 1 order roughly normally. Okay. So, we expect that there will be always a laminar boundary layer that will be established on the droplet for the most part of the process, right. So, the Reynolds number here is basically written as rho g u r drop divided by mu g, right. Okay. So, that you can cross validate that what that number will be. Okay. Now, so the drag coefficient is given by the drag of the liquid or the rate of change of velocity of the liquid is actually a function of the Reynolds number, right. Okay. And this is the equation that actually governs it, this equation and this equation. So, you can solve it and you can find out how the velocity of the droplet actually evolves. That does not require any solution of the internal flow field, right. Okay, because you can just find out what will be the velocity of the droplet, how the velocity of the droplet will evolve, okay, regardless of its evaporation. That is because as we established even with evaporation that RE does not reduce by that much and the equilibration of the velocity happens very fast, okay, very fast the droplet gets entrained into the flow field. Okay. So, the velocity deficit actually reduces pretty fast. Okay. So, this is the expression for the Reynolds number that we are going to use for the gas phase. Now, the velocity of the liquid phase due to internal recirculation is 1 order of magnitude lower than the relative gas velocity. So, if we look at the velocity within the liquid phase, that is velocity in the liquid, not the absolute velocity, do not confuse this with that, these are not the same, UL and U liquid are not the same, right. So, this velocity is roughly 0.1 of the velocity of the gas phase, that means UR, so to say, right. So, roughly about 1 order lower, okay, 1 order of magnitude lower. But as you can rightly guess, rho L is however 10 to the power of 3 times rho g, that is the typical values like 10 to the power of 2 to 10 to the power of 3. So, therefore, if one computes something like a liquid phase Reynolds number REL, okay, that Reynolds number, okay, will be large, will be of the same order. So, it will be either the same as RE, in some cases it can be even greater than RE, right, because you have an order 3 change over here, right. Though the velocity actually reduces by 1 order, this actually increases by 3 orders. Of course, the viscosity also needs to be readjusted, that is also high, okay. But you combine all these things, normally the liquid phase Reynolds number and the gas phase Reynolds number will be very comparable. Okay. Sometimes the liquid phase Reynolds number can be actually a little higher than the gas phase Reynolds number. Okay. So, with that we stop on this lecture, we will pick up in the next lecture, okay, where we will show that how this Reynolds number, where does it come into the picture and how we can actually establish that the droplet actually does not rotate by that much. Okay.